Sí.
Is this involved in USFP?
No, fortunately no. Also started in mostly from the university.
Yeah, no, that one I know. Didn't know there were alternative approaches.
And also with neural networks. And Humboldt University has some collaboration with Brazil and Korea and they
Are you involved somehow with these batch centers?
no. It's also different.
Tenemos que hacer afuera, está mejor que aquí.
There was only what SSP. They don't want to couple it.
Bueno, empezamos. Well, good morning everybody. Today we have Felix Muller with us. He got the bachelor degree and master degree in statistical and nonlinear physics in 2006 from the Humboldt University in Berlin, where he's also currently performing his PhD degree. He's almost finishing under the supervision of Dr. Sistemas. And the title, I'm not sure if that one of the thesis, but it will be related to reaction diffusion systems and synchronization in stochastic coupled systems. So today he's going to talk about the patterns in potassium-driven neural ensembles. Thank you very much.
Okay, thank you very much to invite me here. It's really nice to be here. And yeah, it is related to reaction diffusion systems. The patterns I will show you coming along with a model of reaction diffusion systems. And this work I want to present here is a part of my PhD thesis. And it's about, as you said, patterns in potassium-driven neural ensembles. And it's about activity patterns in extracellular space, where released ions are delivered in extracellular space, and their concentrations of potassium, in my case potassium ions, form chemical waves and in turn influences back the neural behavior. I will start here with some experimental background, philological background, what the role of potassium for cell dynamics is, why we want to study it. And then I will give a short scheme of heterogeneous media, which is the base of our FNK model, that's what we call it. And I will show you attractors and bifurcation of the local model, and then I want to extend the model spatially and present you activity in a binary medium. Okay, first, I picked one of a number of papers about the topic of potassium in cells. This is a work from 2008. And first, it is important to know that a potassium level beyond the equilibrium level within neural tissue always strongly influences the excitability of the neurons in the environment and can lead to a different behavior, oscillatory behavior, or even at higher potassium level to a complete blocking, a frozen state, which seriously can damage the cells. And in literature, it is also discussed that this may be the origin of diseases like epilepsy or malfunctions like spreading depression. Here in this paper, this potassium accumulation hypothesis was shown. So when the potassium level is perturbed by noise, by intrinsic noise in the neural tissue, beyond a certain threshold, then it starts growing until a depolarization block. And it is assumed that a not very well established feedback mechanism is the origin of that. And after that block, after some minutes of this frozen depolarized state, the cells would die and cannot perform any excitability behavior anymore. So this is a scheme of the extracellular potassium dynamics about the processes here. We have 3 cells and extracellular space between them. So we have pumps on the membranes which transport ions in and out of the cells and deliver, in this case, I want to concentrate here on this potassium ions into the extracellular space. We don't want to consider any synaptical connections of the cells because the time scale of the synaptical processes are much faster than those chemical processes here. So we will model them as white noise, and we are only interested in the indirect chemical coupling via this exterior of the excitable units. So the dynamics of the exterior concentration is given by such a balance equation with the source term here for delivering the ions out of cells, and of course a decay or diffusion term which account for all the transport processes to the environment. Okay. Potassium in the extracellular space is released when the membranes are excited, and we want to model the excitation of such membranes with a very known FitzHugh-Nagumo equation, with a very known FitzHugh-Nagumo model here consisting on 2 equations: the activator equation and the inhibitor equation, with the main parameter A here to control the excitability of the system. So this is a phase space plot here. The blue line corresponds to the node line of the inhibitor, and the red to the node line of the activator. And the closer this node line controlled by the parameter A is to the hot bifurcation point, the easier the system is superthreshold excitable. And this is done in our case with a fluctuating threshold parameter. We add white Gaussian noise on the inhibitor equation with the intensity D here, and that leads to the stochastic occurrence of spikes here in the phase space correspond to a large excursion in phase space, first to the active state on the right stable branch, coming back to the left stable branch, which is a refractory state, and then finally to the rest state here.
This is for A naught equal to 1?
Almost 1.05 or something, very close to the Hopf bifurcation point. Exactly, the Hopf the critical parameter would be 1. Mm-hmm. So this is the first setup for the equation is for an excitable system very close to the Hopf point. We have an additional function here for separating or for separate control of the time scales being at the activated or on the refractory or rest state, or let's say activated and non-activated state. Here tau L is the residence time on the left branch, and tau R controls the residence time on the right branch. Okay.
Sorry, what is XS? Where is it located?
This XS is the smoothness, let's say, of this step function. This step function is.
Sorry, it's not. Yeah. This goes not to
no,
so it's at 0. So the transition between the two regimes at 0. X equals to 0.
Exactly. Mm-hmm. Yeah, we somewhat divide the space in x larger than 0, which is active, and x smaller than 0, which we account for non-active behavior. Mm-hmm. Okay, now we want to couple this excitable dynamics to the exterior. We introduce a third variable z here, And this leads to such an additional equation for that. That corresponds to the balance equation I've already mentioned, now in a dimensionless form. So the zero level, the equilibrium level of potassium concentration now is at Z equals to 0. And here we have again a source term with a release rate alpha and the function g of x that actually detects whether the neuron is excited or not. When the neuron is excited, then x is larger than 0, and the g is almost 1, and for the rest state, g would be 0. And a decay term with a decay rate beta here. As you can see, z in this case is always non-negative, and it enters here in the inhibitory equation in this form. This form C is the coupling to the exterior, which is also always positive. So the higher the Z level is, the smaller the effective threshold parameter would be, and that can lead to oscillatory behavior that we go beyond the Hopf bifurcation, or even to a second I-stable point at very high Z. So these are here the 3D phase portraits with some sample trajectories here. The black line is still below the Hopf bifurcation, so this spirals back to the lower fixed point. But for the red line here corresponds already to a stable limit cycle at a certain Z level. Even higher coupling to the exterior would lead to an even higher limit cycle, the red one here, to at a higher Z level, and for even higher coupling, this situation would end up in the upper stable state. And this upper stable state corresponds already to this completely depolarized state, where the units remain in the active part of the activity. Okay. We can also interpret those three equations as delay equations. Formal integration of the Z dynamics would give this integral equation with the decay term and this integral part with a memory kernel, which can be approximated when we forget about the initial conditions as such a simple expression. And then the inhibitor equation would take this form, where we have a function with a delay for d here. So we could interpret our three-component model also as a two-component model with delay. But this is only a small excursion because you are the experts of delay equations, and I just want to show you that our model could be interpreted as delay equations, and it's not so far from delay.
What is the time scale of the delay of TV?
This tau d here?
Yes.
Here are a bit more approximations in it. It's not only about forgetting the initial conditions, but it is assumed that finally this tau d is a certain memory length, and it counts or it measures whether the unit is in the past active or not. It's an additional arbitrary parameter.
But probably depends on the parameters of the system, I guess, and on the dynamics of the system.
Yes, of course. Of course. But it not only comes from the parameters. It's not intrinsically given. So in this case, it would be arbitrary.
Okay.
So now it has infinitesimal dimensions, infinite dimensions, and therefore the three-component system, a set of two systems of two equations, but it's infinite dimensions.
But this is very interesting.
You have three-dimensional.
So,
okay, but this is only a short excursion.
Linear force system. No, a linear force system.
Is dat force is autonomous?
There's no
It's-
Well, you can
It
consider
was
some
not-
more. You go back.
Okay, it was-
Is z dot equals to alpha g.
Uh-huh.
You consider the interested force for g.
Yes.
Special names.
Or force minus
Mhm, mhm.
But x of t is independent of z. No, it's coupled to z. But you make
It is assumed that the delivering needs a certain time and the influence back to the neural behavior needs a certain time, and finally it is a different approach to
But if you make a standard adiabatic approximation, z will be equal to alpha g over beta.
You have to integrate g over the activity. Or what do you mean?
No, when you make this approximation, you make this independent of the other equations. So you only take this equation, z dot equals to alpha g minus beta z. And then you make an interesting approximation, which I was not aware of. And instead of saying that z relaxes to alpha g of x over beta, which is the other
Yes.
approximation,
Which is not stationary.
Yeah.
okay, no, because x is not a stationary,
Yes.
x depends on time.
But
As we said, this can be improved by introducing a duality. You said that if I have this equation, z dot equals to alpha g
Yes.
minus beta, I could write z, adiabatic approximation, z equals to alpha g of x of t minus beta. Okay? That would be a standard and easy to understand approximation. And then you tell me that I can improve this approximation by including the delay time.
No, this is just the formal integration. Okay, up to here it's true, but now we simplified.
Well,
this is the integration of theta. You go, look.
I think that's better.
You have this z dot equals to alpha and g of x of t minus beta z. A standard approximation would be, okay, z of t approximately equals to alpha over beta g of x of t. Okay. You're telling that this can be approximated, so less wiggle, by inducing alpha beta g x of t minus tau t. That's what you tell me. This is better than this.
Well, here he's integrating the equation. You are taking the adiabatic.
I don't care how he gets the result. I mean, tell him this is better than this.
Why?
I don't know, that's what I'm asking.
So,
Because
One is only the adiabatic
elimination is that not a function of t. Well, it is because it in a slower time scale. So
Yeah, but that's correct.
So this could be
for the adiabatic from the adiabatic elimination, this would be either 1 or 0. Let's say for a step function.
yeah, but
So we have
I'm asking why should I use this instead of this? Which is the advantage of using this equation instead of using this equation? Which is the advantage of the improvement? Is there an improvement or an advantage?
Yeah, but this equation contains. Yeah, okay. Yeah, now I see your point. Okay. Okay, so we assume that it needs a certain time.
But this is very general, this is just for this kind of problems. Because your only starting point is the equation upwards.
Okay.
Can I use this trick in many other cases? Because I want to start to use it. If possible.
This is much better.
No, this is completely forgotten about. I mean, everything is decayed. But in the meantime, neuronal behavior could change, and this somehow take it into account because.
Yeah, exactly. So that is better if the time scale, if the adiabatic elimination is good enough, but you still want to keep some memory of time off.
Yeah.
Then I guess the intermediate. So for the adiabatic elimination, the time scale of one equation has to be much faster than the other one. It's not that fast.
Maybe this is it.
If you want to do that, you put multiple time scales
Exactly.
and do the things in a control fashion. In a control. I don't understand the reasoning.
I guess phenomenologically you can say that if you have a time scale for the response of that variable that couples to another one, you get an effective delay. That's what he is trying to say. Roughly, not what he
Who sets this time
says.
scale?
To accompany,
So, but who sets this time
I
scale?
get the characteristic time scale of the field that couples the two. So I guess in the previous question would be that beta, no? Beta.
Which includes the decay.
Now, my point also is that when you have a delayed system, there are many effects that can appear,
Yes.
like chaos, which cannot appear in the original equation.
So you have the equations.
It's
Well,
not
no,
the
it's only the
simple
simple
form. No, it's
It's
not
only
the
one
simple
equation.
form.
Yeah, that's right.
Only one.
Well, but it's coupled to the x and it was coupled to
With
the
the
z.
short-
Two component systems, including delay, of course, it's a large range of behavior.
So I'm asking how controlled is this approximation? Is it uncontrolled approximation or is how controlled is it?
how controlled.
Yes. Can you control the goodness of this approximation?
No, we just did it formally, to be honest. Yeah.
And you have a formula for
We didn't check for which delay times we are in the same scope.
and you have a formula for GD? Is there a explicit formula for GD?
The formula of what?
GD.
The delay time.
No. We just give the time delay as a certain memory that we include a possible range of active or inactive states of time. But I want to continue with the three-component model. And here I want to show you the bifurcation diagram of the control parameter C about the coupling to the exterior. So here you can see for very low C, the system behaves almost like the two-component FitzHugh-Nagumo model, with one lowest fixed point here at z equals to 0, and behaves in an excitable way. But at a certain point, a stable and an unstable limit cycle appears, bifurcates here, and then we have the coexistence of two attractors. So by noise, as you can see here, x over time, activated over time, the system can perturb by noise beyond the unstable limit cycle and gets attracted by the stable limit cycle and performs oscillatory behavior. For increasing the C, we can even have three stable attractors in the system, because there's another upper fixed point now coming along with the stable limit cycle and the lower fixed point as well. So depending on the initial values, we end up in such.
So, can you explain a little bit more the diagram? I mean, this appearance of stable and unstable limit cycle, as you say, in a certain number of cycles, it's to what is it connected? I mean, is it connected to a bounding point? I mean, there's a reverse of stability of a Hopf, or?
No, it's not a Hopf bifurcation point. It's like from the other side would be the annihilation of the stable and unstable cycle.
Yeah, but I mean, this point is not generic. For instance, it happens when you have a reverse of stability of a Hopf from forward to backward, from supercritical to subcritical. For example, so
you
have
mean
something like
this
that?
point? Or
Yeah.
This point. Mm-hmm.
So do you have a reverse of the stability of a Hopf point? I mean, going from supercritical to subcritical?
No.
No.
No, we haven't. No. I mean, maybe it's better to. I mean, these plots are somehow it illustrates the dynamics exactly here. Or maybe in this point, here we have also an unstable limit cycle in between, and that makes the directions to go to the upper stable state. That corresponds to this.
But for instance, if you go, I mean, these two lines that go apparently touch at some point when C goes to, I don't know, 0.2 or something like that. Do you know what
those lines. So this is an unstable fixed point here.
Sorry.
And this would be a touch.
Here.
Yes.
Ah.
This unstable limit cycle behaves like this unstable limit cycle and touches this branch via subcritical bifurcation. This is subcritical bifurcation. And for very low C equal to 40 in this case, even this curve, of course, would close the stability lines. But we don't consider so high coupling because it's not beyond scope here. So okay, beyond the existence of a stable limit cycle, and now we have the following behavior. At the moment where the system which is in the lower stable fixed point is perturbed superthreshold, it starts spiking, and this spiking leads to a growth of Z level. But this in turn influences and forces the spiking, and finally the shape of the spiking changes. More and more, the unit is close to the stable active branch, and finally it spirals in the high potassium value, where all the units would be frozen in the depolarized state. So this could be a qualitative explanation for this potassium accumulation hypothesis. That line corresponds to the line I've shown you in the experiment. Okay, now this was the local dynamics. Now I want to come to the lattice approximation, to a spatial extension of the model. The first approximation we want to perform, just to make life easy, randomly distributed cells, which are marked here in blue, randomly distributed cells with active membranes in the neural tissue are now considered as a regular lattice with a yellow extracellular space. But still there are two different regimes to distinguish, or two different setups, let's say. First are the embedded units. So we have a binary medium with directly embedded active units within the extracellular space. So it's divided, it's a heterogeneous medium. The second case is a two-layer situation where the Z can diffuse continuously, and on a second layer, the active units can communicate with the Z level and can influence each other chemically via the medium. We decide to set up the binary medium, or I will show you here the results from the binary medium. We compare it also with the two-layer situation, and found finally the same activity patterns at different parameter values. So now we have such a lattice. The gray cells here represent the FitzHugh-Nagumo units, and the white cells are for the extracellular space, governed by the Z dynamics given here, now in a discretized form. Again, the release rate, which counts maybe for this cell how many units in the environment are active or not. The diffusion, which only takes place in the white cells, and the decay term.
You already assume over the state neighbors of each?
We test a couple of situations, and finally we found, okay, at least for this sum, for this neighborhood, we can always rescale it by the value of the parameter of the diffusion. And for this neighborhood, this neighborhood can account for a direct neighborhood or also for a larger neighborhood, but this can also be scaled by the alpha. So you can of course also make it in a global way. So then of course situation changes, but when you are local, you can scale it. I just want to give you a short overview over the used parameters. First, we only vary the external parameters, so the release rate, the decay rate, and the diffusion. The characteristics of the excitable units are somehow the same, except of the noise realizations here. We give them, of course, a certain noise intensity, and then with a certain realization of spike occurrence. And I want to present the sets in the order of rising Z level. So I start with a situation where the decay rate is so high that the Z is very fast decayed, and the single units remain somehow in the excitable state. And then we observe what you can see, maybe one word to the color code. What you can see here, blue means zero level in Z, and green, yellow, and red is the rising Z level. And what you can see here is gray and black dots are the active units embedded in this medium. Gray means inactive and black means, another way around, sorry. Okay, gray and black is the same, just because of the color code, and white means active cells. So in the small environment of an active cell, that is released, and that leads to propagating waves and spirals as found in two-component diffusively coupled reaction diffusion systems. And here I want to show you a little movie. Once such structures are nucleated, they start propagating as also wave segments, and now I decrease the decay rate, and waves curls up and form spiral activity and larger patterns.
You have periodic boundary conditions.
And these are periodic boundary conditions, right? Mm-hmm. Okay, these patterns are known, but now I will come to traveling clusters sustained by noise. The former set, or the former activity patterns were not supported by noise, they were just nucleated. Once patterns are nucleated and with such periodic boundaries, they never disappear, and they are self-stabilized. But here, these spots I want to show you first with absorbing boundary conditions, which is a bit more interesting, maybe, are noise supported. So we have activity clouds here traveling over the medium erratically and can decay again. And can decay or vanishing when reaching the boundaries. And those activity patterns are found for different ions in cells, like from calcium dynamics. Experiments with calcium dynamics with certain buffers show very similar activity patterns. This is a situation for a very similar parameter set, but with periodic boundaries. And here, situation is similar. These clouds, these puffs appear, but they don't have enough time to start propagating. But what you can see is this modulation, a global modulation induced by the parameters of the whole medium. And as you can see here in neighboring cells, this is an active unit, and this is a neighboring Z element, and the Z follows in a nice way the oscillations or the spiking. It's not oscillatory, it's still excitatory, but follows the spiking of the neuron in the neighborhood. And what you can see is this, at least almost half of period of this global oscillations. Coming to a higher ZC, now the neurons, the active units, have the possibility to heave up to the limit cycle, to a stable limit cycle. As you can see here, again by noise. And when the noise is so small that for this size of the medium, the enucleation probability is really low. Once one cell starts oscillating, it delivers that into the extracellular space and forces all the other neurons also to follow the synchronization, so they fire in a very synchronized way. And so thus we have a bistable situation before everything is in rest, and then the oscillatory wave comes, and this could be also interpreted as plasticity of the neurons. And the last set I want to show you is a complete depolarized state. This is now for the highest level of Z, for a very high release rate, so the medium is flooded by the potassium concentration, again in a bistable way. This is a rest state here, and this is a upper stable fixed point. And within such spots, all neurons are in this frozen depolarized state, and that would lead finally in a biological interpretation to cell death. But the situation is not so frozen when we put noise on it, because then noise can shape inverted patterns into this high-level ZC and form such nice traveling waves, or also in the snapshot here, spirals and so on. So all the patterns what we have had for the first parameter set from the lower fixed point, now they are coming from the upper fixed point, like inverted patterns. Okay, that was the last set I want to show you. I just want to quickly conclude. I presented this three-component model for neuron units coupled via the external medium. I discussed the local behavior by presenting the attractors and bifurcations, and then in the extended model by the variation of the external parameters, we have seen a lot of different activity patterns which cannot be obtained by a two-component diffusively coupled reaction diffusion model. This is published here in this PRE 1 year ago. Just one slide. I just want to quickly give you an overview over my further research topics. That was probability density propagation and velocity fields. It was a Fokker-Planck equation approach. Then also nucleation rates and patterns in reaction diffusion systems, as we have seen already here. Also in heterogeneous media or media with defects. Then transport and synchronization, oscillating periodic fields related to ratchets. And also synchronization and coupled excitable two-state units with a delayed feedback. And now my last topic is boundary effects in noisy bistable and excitation front dynamics. Okay, thank you very much for your
questions or comments?
See, what would be the difference between this model in which the cells, you have cells and then the medium, so you have it's a discrete, heterogeneous media. Wouldn't it be the same outcome if you put a continuous media of the two-component FitzHugh-Nagumo coupled to a third field which is also homogeneous? Physically homogeneous?
The homogeneous.
Yeah, but is there any wrong in having the discrete cells? Is doing something on the results?
Phenomenologically, the difference is that you cannot find any patterns like those clouds and clusters, and this is due to the action of finally, the extracellular space is modeled with a passive medium. This is not an activator or an inhibitor. It's just a passive medium which influences back the active units. So, and while they are not directly coupled, we have always a certain delay in the occurrence of those patterns. So this is of course the main difference. And
in the two-layer systems, I don't know, you showed the...
Yeah.
Did you comment the results? I mean, is that a mean field approximation? I don't know.
No, it's not a mean field approximation because the units, you mean this second setup, right?
Yeah.
It's fine. It's not a mean field approximation because the Z still is diffusively here. And also the units, this unit doesn't interact with this unit in the same time. So that it's still a max neighbor or a local model. But here we have seen one pattern, a localized pattern, maybe I have it here, which we did not obtain for the embedded model. This is the oscillon, or I call it oscillon. This is a localized structure, and now the units are not embedded; they are on a second layer. And this is a structure which is feeding itself, but then propagated out. It stays localized, but oscillates in between.
Another question? Well, if not, thanks again. He will be around this afternoon, so if anybody wants to talk to him, it will be until maybe 5 or something like that. Then he's traveling back. If he's lucky, he will be back in Berlin this afternoon.
Sì, lo che quería comentar también es que, bueno, un poco después de terminando este caso,